Hello, welcome you all. Just a minute. Okay. Okay. So, welcome you all to the sixth problem solving session for this course titled Multirate-DSP. So, if you have followed the lectures for week 6 closely, just a minute. Okay. These following things have been covered. So, instructor have analyzed M channel, maximally, decimated, filter banks, specifically, to be specific, M is equal to 2 has been analyzed extensively. We have also seen the equivalent transfer function, the transfer function which in terms of course the input output relation. We have seen synthesis filters and analysis filters. The basic takeaway from that discussion is that you have this signal component and aliasing component, and your main goal is to remove the aliasing part, of course, to able to enable perfect reconstruction so that you can get your original signal back. And we have also seen the discussion regarding pass band and stop band of these filters. We have also seen that what amount of deviation is allowed in pass band and stop band, of course, which are practical scenarios. You cannot have ideal brick wall kind of response. We have seen the concept of transition band, of course, and actually today's one or two problems involves the concept of transition width, so we'll see in more details. So with this, let us move on to our first problem. So okay, there is some problem in ordering. This should be the first. Okay. So let us see the question. Ask that which of the following is or are the conditions for a, there is a typo here, it should be a type 1 linear phase filter of order n. So again, if you have followed the lectures, actually it's a very straightforward question, can be answered in a second or that, but as of now I am avoiding that. We'll see, since the question arises, we'll move into the concepts of different type of linear phase filter, and I'll write them down for revision purpose. So let me write down linear, this order n is finite, therefore the filter in question is linear phase FIR filter. FIR refers to, of course, finite impulse response. This is because n is finite. We have seen that if the filter is of order n, generally the length is uh, just one more unit, that is n plus 1. That is if a filter is of order n, it suggests that length of filter is n plus 1. Actually, you can see that from the, let me write down the discrete time impulse response, that is Hn, H naught, H1 up to capital N, since it's a filter of order n. So if you calculate the number of coefficients, there are n plus 1 coefficients. Sometimes it's called n plus 1 tap filter, because their tab refer to basically number of coefficients of the filter, impulse response of the filter, of course. And if we take the Z transform of this Hn, that earlier in problem solving sessions we seen that n runs from minus infinity to infinity, but since it's a practical causal filter, this arrow indicates it the position of 0th index. Your n no more spans from minus infinity to infinity. It starts at 0 and ends at n. The rest of the things remains kind of same. So you get your Z transform. If I simplify it further, something like this. No, sorry. To H capital N Z to the power minus n. Now, since the question, the problem in discussion considered with type 1 filter only, but let me just write down the specifications for all the filters. So they varies mostly in 3 aspects. That first one is the order of filter, second one is length, but anyway that's not something independent, it just depends, you can consider it to be a derivative of order itself, because if your order is n, then your length is just n plus 1, so that's a redundant column, but I'm still writing it for better understanding. And third property is symmetry of impulse response. So actually there are 2 parameters which varies across different types of linear phase FIR filter. First one is order and second one is centered around the symmetry of impulse response Hn. So we are talking about type 1 linear phase FIR filter. These are the filters which have this even order. Even order just translates into odd length. You can see if n is even, n plus 1 is going to be odd, and the symmetry of the impulse response is even. Even symmetric basically means, let me write it down here, it's symmetric around the center point, just in an intuitive level. Mathematical, if channel, sorry, the filter of uh, length n plus 1, of course, then this is the condition actually, h of 0th index is going to be, the first coefficient is equal to the last coefficient, the second one is equal to second last, like that. This is called even symmetry. Type 2 are those linear phasor filters which have their order to be odd, length from this translate to even only. Symmetry, however, remains same. Type 2 linear phasor filter have their impulse response symmetry to be even. Now this symmetry changes from type 3 onwards. For type 3 filter, order is even, length is odd, and symmetry is going to be odd one. Odd symmetry can be from corresponds to this scenario. Odd symmetry is also termed as antisymmetry. Just another name. It corresponds to this thing actually. H1, the magnitude of course remains same, and the sign changes. It's something like if you flip the coefficients across the center in opposite direction with respect to horizontal axis and discrete time axis. So that is the case actually. We'll see that in greater details later. And last we are concerned with type 4 filter, which has its order to be odd and length to be even. Of course, that comes directly from odd order, and the symmetry of response is odd only. So we can see from this table that type 1 is a filter which have even symmetry in impulse response, and the order is also even. Therefore the second option is correct. Let us move to our second question. You can see we have given a discrete time signal, sinusoid, and the question asked that which of the following is true about 8-point DFT of signal. So we are well familiar with DFT equation. The immediate thing that may come to your mind that I should compute 8-point DFT of xn and check manually which of the it's basically asked that which of the frequency components have zero magnitude and which one of non-zero. So for that you need to maybe you want to do some brute force DFT computation and check the different frequency components individually. But one simple way to do sorry, not simple actually, you can do it by brute force. But brute force is good when you have like 2 or 4 point DFT. If you move towards higher points, then your brute force is not very helpful for you because your computation becomes really expensive. So brute force computation. In exams you often don't have time to compute the DFT completely. And that's not the correct way also. So brute force DFT computation is not recommended. So you need not only solve the question correctly, but you need to solve it in an efficient manner so that you can save time. So brute force DFT computation is not recommended at all. So let us write down the first the endpoint DFT. Endpoint DFT of xn is written as follows. So you can see this is the your kth DFT coefficient. If you remember from the lectures, DFT basically takes a endpoint input vector input vector of dimension n and do some processing on DFT matrix, which is n cross size n cross n, and it provides you a output vector of same length, that is of n. So xk we denote as kth DFT coefficient. It's just a weighted combination of these symbols xn. Of course the phase is different. Oh, by the way, the wn is just an abbreviation of this. So if I elaborate it on little on it, it becomes this: x of m to the power minus j 2 pi k m over n. So one good thought is that you can compute this DFT coefficient, k point 8 point DFT coefficient, all these 8, but that's not a good way. So let us write down the endpoint IDFT also. That actually brings you from frequency domain to time domain. So it's another way of writing xn itself. IDFT computation involves bringing this normalization terms. Sign just changes, nothing else really change. And this question we have n is equal to 8, so your xn is therefore can be written like this: 1/8 m runs from 0 to or minus, sorry, no minus is there. If you expand this equation, it will result into this. The first DFT coefficient corresponds to x0, the exponential just vanishes. The second one corresponds to frequency of 2π/8. Similarly, second coefficient. By the way, DFT coefficient can be written in like xk also, and xk, it's just a matter of notation only. 4πn/8. Six by n/8. Hello. Uh, you can. I guess you can hear me now. There's some malfunction in the headphone. It's working correctly. Oh, sorry for the inconvenience. So we are discussing this. Yep. So this x4 corresponds to frequency component 8 pi over 8 x5 corresponds to a to the power j 10 pi n 8 x6 to the power j 12 pi n over 8 plus x 7 is the last component corresponding to the highest frequency of 14 pi over 8. Okay, so this should be the expression of xn, the input signal, in terms of its 8-point DFT coefficients. So now let us use this tricky way to represent xn. Xn is given as pi by 2 sine 2 pi n over 8. Now we use this property that sine omega n can anytime be written as the linear combinations of exponent to the power j omega n minus e to the power minus j omega n over 2j. So let us use the property 1 here. So what we get, pi over 2 e to the power j 2 pi n over 8 minus e to the power minus j 2 pi n over 8 by 2j. If we break it down further, it becomes pi over 4j magnitude times e to the power j 2 pi n over 8 minus pi over 4j e to the power minus j 2 pi n over 8. Now let me highlight in different color that okay, this term corresponds to this term. So fine, therefore the coefficient corresponds to frequency 2 pi over 8. The x1 should have this value. So there is a frequency component at pi by 8. Let me write it down. There is a frequency component at omega is equal to 2 pi by 8. Now a very common mistake is that you see this and you see that e to the power minus j 2 pi n over 8. You see that for xn expression there is no negative frequency, and you jump to the conclusion okay, therefore there is only one frequency component at 2 pi by 8. It matches, and you take the fourth answer as the correct one. But I urge you to carefully look into this part also, because this is still existent. And let me play a small trick here. It's not a trick exactly, it's a way of writing it differently. You can see that e to the power minus j 2 pi n over 8. Can we do that? A to the power j 2 pi times a to the power minus j 2 pi n over 8. Can we write that? This is very important. What is the value of this? This corresponds to, let me write here in the below, this is nothing but cos 2 pi plus j sin 2 pi, that is 1. So I'm writing this. You can write that this is just value of 1. When you bring inside this, what it becomes? (16 pi minus 2 pi times n by 8 to the power j 14 pi over 8. See, you must, even if there is some negative frequency and your xn expression, the IDFT doesn't contain a negative frequency, you should try to look into the corresponding positive frequency, because e to the power j 2 pi n 8 is nothing but e to the power j 14 pi 8. You can see that, because this discrete time frequency, you must always remember it has a periodicity of 2 pi, so it's keep repeating. So that may not be obvious, but the frequency of minus 2 pi by 8 is just 14 pi by 8. So therefore this term, you can write it as j 14 pi by 8. Now you can see that this matches with the highest frequency in the expression of xn. Therefore x7 is this value of pi over 4j, sorry, minus pi over 4j. So what is the conclusion? That xn has two frequency components. At pi 2 pi by 8 and another is 14 pi by 8. You see this, do you see this, these frequency components are present in the expression of xn. Therefore all these DFT coefficients starting from x0 to x2, x3, x4, x5, x6, they all goes to 0 actually. And what is the value of x0? You consider this normalization factor outside, that is let me write here x0, the DFT coefficient, the first DFT coefficient, which you can also say to be DC term, because see, it corresponds to frequency of 0. Therefore it's a DC term only, DC portion of the sequence xn. So x naught over 8 is pi over 4j, just becomes, it just results into 2 pi over j of x naught. Similarly, you can say x7 is minus 2 pi over j. So the frequency component corresponds to, there are only two non-zero frequency components at omega 2 pi over 8 and omega 14 pi over 8, and nowhere else for this particular signal xn. Therefore the third option is true. Let us move to our next question. The indexing are wrong. It's a third question. So the question asks that which of the following is not suitable to be considered as either low pass filter or high pass filter, and the answers are, you see the answers, you see the first answer is like Hn, odd symmetric and odd length. So the answer should be in terms of the properties of impulse response. So this question this problem asks to verify the nature of filter from the properties of its impulse response. So we will try to understand by a few examples. We will go through one by one by these all options, construct a small example, and try to see whether the resulting filter is going to be a low pass filter, high pass filter. Before that, let us draw the spectrum of low pass filter, because we want the question is concerned around a filter which is neither a low pass or high pass. So for that we must understand what is low pass filter and what is the high pass filter. So the resulting filter is not supposed to satisfy any of their properties. I know that we have seen multiple times the spectrum of low pass filter, and consider this as a revision only. So practical low pass filter has this kind of response. Of course, ideally it should be like that, this kind of brick wall, that it allows frequency up to this range and cut off the higher frequency starting from this only, but that doesn't happen. So this part, this is actually where your pass band ends, and this is where your stop band actually begins beyond a certain level, and in between you always have this transition band. So we'll consider this in some later problem. Let us focus on this part. So this low pass filter, what is the characteristics? You see, it allows frequency components close to 0, which is DC value, of course. So it only allows the low frequency component of signal. Therefore its spectrum, this only in this range, starting from the DC value up to a certain frequency component, it is going to allow only low frequency components only. And pi, which corresponds to, of course, the high frequency, and it generally the spectrum, the passband edge, actually this is passband edge, that represents up to what frequency your filter is willing to pass. So that actually for practical purpose it ends pretty early compared to pi. So that is the nature of low pass filter. On the other hand, high pass filter is not at all concerned about the frequency components which are close to DC value. That is, it do not allow the DC or the low frequency components, and it's only allow the high frequency components. So intuitively its frequency response is something like that. It stop band starts actually from 0 onwards, and it started allowing frequencies which is much far from the 0 value. So in some way it's completely opposite to the low pass filter behavior. In low pass filter you can see it allows the DC value and the nearby low frequency components, and its stop band starts attenuating the frequency components much earlier than reaching pi. It started attenuating components from here only. On the other hand, this high pass filter, it completely cuts off the low frequency components, and it only passes the high frequency component. This pi refers to high frequency. So it intuitively it only allows frequency components which are around pi. So the filter in question is neither low pass nor high pass. So for low pass filter, if I am concerned around the frequency response at omega is equal to 0, it is 1. On the other hand, for high pass filter, the frequency response, as you can see from the spectrum drawn here, omega is equal to pi, it's 1. So filter in question, since it's neither high pass low pass, it should have frequency spectrum such that at omega is equal to 0, the filter should not allow any components of signal, that is its spectrum is 0 at omega is equal to 0, and its spectrum is also 0 at omega equal to pi. Its spectrum is somewhere in between, but neither it is going to allow the frequency component, the actually frequency component of correspond to omega is equal to 0, that neither it is allowing to pass the DC value, the DC component, or the high frequency component. So let us proceed one by one. In first case, your Hn is odd symmetric and odd length. Now odd symmetric corresponds to this property, that is h of n should be minus h of n minus n for n 0 up to n. And this corresponds to a filter of length n plus 1. Now for odd length, that is n plus 1 is odd, therefore n is going to be even. Therefore this equation for n is equal to n minus 2, the tap or the coefficient at the center, what does you put small n is equal to capital N over 2, what do you get? Minus hn minus capital N over 2. You bring it on both sides, it suggests it should be 0, that the coefficient at the center should be 0. If your impulse response has odd length and also follows odd symmetry, it's going to have the center coefficient to be 0. So let us consider the easiest example of odd length filtered, where n plus 1 is 3. Therefore hn we write as minus 1 0 1. Remember, the center component must be 0 because we have already established that. If I draw the impulse response here, it will look something like this. 0. This corresponds to 1. This is 2. It's minus 1. This is 1. So what is the spectrum of Hn? Let me write it here. H E of j omega z transform n runs from 0 to 2 Hn to the power minus j n is equal to H0 plus H1 to the power j omega H2 to the power minus j 2 omega. Now we put the value of H0 we see as minus 1, H1 as 0, so it vanishes, and H2 is 1 e to the power minus j 2 omega. Therefore the value of h e to the power j omega at omega is equal to 0 equal to minus 1 plus e to the power minus j times 0 minus 1 plus 1 0. So this is not a low pass filter, not a LPF. Now I have to check the high pass filter criteria. So let me add a slide here. Okay, so remember this expression of h of e to the power j omega, and let us move to, we have seen that it is not a low pass filter because its spectrum is 0 at omega is equal to 0. Now we need to check its value. Let me write that h to the power j omega expression here again, minus 1 plus to the power minus j 2 omega. Okay, therefore the value of the spectrum at omega is equal to pi is minus 1 plus the power minus j 2 pi is nothing but 1 again, so this is 0. So not a high pass filter. Okay, so Hn odd symmetry, odd length, this property satisfies it implies the filter is neither low pass filter nor high pass filter, but we need to check the other cases also. Second case is the Hn even symmetric and even length. Hn shows two property, even symmetry, even length. the way this corresponds to type 2 linear phase FIR filter. If you remember from our previous the first problem we encountered today, and our first case forgotten to write odd symmetry and odd length. This actually corresponds to type 3 filter. Let me just revisit. Yeah, it's type 3 only. Type 3 linear phase FIR filter. So this is of even length and even symmetry, so the coefficients on both end should be equal, and we are not really concerned with these two coefficient in middle. If we consider fourth length sequence, fourth length filter of length 4, this is it. I draw the impulse response here. It turns out like this. Even symmetry, you can see it's a mirror image of each other, correspond to vertical axis with respect to vertical axis. So for this, let us write down the spectrum again. Here n ranges from 0 to 3, Hn to the power minus j omega n. This is H naught value is 1, that is the component. H1 value is 3, corresponds to this frequency omega. This corresponds to frequency to the power minus, corresponds to frequency 2 omega, and this last coefficient is 1, corresponds to frequency 3 omega. Now for this one, let us check whether it's a high pass filter or not. Omega is equal to pi, become 1 plus 3 to the power minus j pi plus 3 to the power minus j 2 pi plus e to the power minus j 3 pi. Okay, again my voice is okay, it's audible now. Fine. Let me write down them in clear manner. So e to the power minus j pi corresponds to -1, therefore it becomes 1 minus 3. E to the power minus j 2 pi corresponds to 1, therefore it is 3, and e to the power minus j 3 pi again corresponds to -1, so it's 0. So not a high pass filter. Let us check whether it's low pass also. But j omega value at omega is equal to 0. It becomes 1 plus 3 plus 3 plus 1, that is 8, therefore not equal to 0. So it's a low pass filter. Therefore, although it's not a high pass filter, it's a low pass filter. So this filter doesn't satisfy the criteria of the filter in question, because it concerned around, it should be neither a low pass filter nor high pass filter. So let us move to our third option, where Hn is even symmetric. Hn satisfies these two property, even symmetry and odd length. If you remember correctly, even symmetry and odd length corresponds to type 1 linear phase FIR filter. So let us consider its impulse response to be 2, 1, 2. Let us draw it also. So length 3, which is odd, and therefore we get the spectrum h to the power j omega as n is equal to 0 to 2 Hn to the power minus j omega n, which corresponds to DC component 2, frequency component 1 corresponds to frequency component omega, and the coefficient 2 corresponds to the frequency 2 omega. Let us try to find its response at frequency omega is equal to pi. 2 plus e to the power minus j pi plus 2 to the power minus j 2 pi. So this is 2 minus 1 plus 2, that is 3, not equal to 0. Therefore it's a high pass filter. Its spectrum is not 0 at omega is equal to pi. Now we can safely avoid checking whether it's a low pass filter or not, because it's doesn't satisfy the criteria of being neither LPF nor. Okay, let us check at what is the response of it at omega is equal to 0. It's nothing but the summation of the coefficients only, 2 plus 1 plus 2. Becomes 5. Therefore it doesn't satisfy the criteria of if its a response at frequency omega is equal to pi is also non-zero, and its response at omega is equal to 0 is also non-zero. Therefore it doesn't satisfy the filter criteria mentioned in the question. So let us check our fourth option. Before that we need to add a slide here. Okay, our last option to check is the fourth one. The fourth case Hn has two property: odd symmetric and even length. Okay, fourth case Hn shows two property: odd symmetry and even length. Therefore you can write its impulse responses like that. Let us consider the length to be 4, so the first and last component should differ in magnitude. The second and second last show the same behavior. So your impulse response can be drawn like this. This is -2. This is 1. This is -1. And this is 2. Response to 0, 1, 2, 3. By the way, let us just revise what observation we have. Okay, we'll have the observation after this only. Let us write the spectrum here. that is from 0 to 3 hn to the power minus j omega n. This corresponds to minus 2 plus the power minus j omega minus e to the power minus j 2 omega, so 2 omega, and e to the power minus j 3 omega. So let us check the response of the spectrum at omega is equal to pi minus 2 plus the power minus j pi minus the power minus j 2 pi plus 2 to the power minus j 3 pi minus 2 minus 1 plus 1. Minus 2. Therefore we obtain it as minus 4 equal to 0. Therefore you can say it doesn't satisfy the criteria of not being high pass filter. Let us check its behavior at omega is equal to 0, comes out to be minus 2 plus 1 minus 1 plus 2, which is 0. So although it's not a low pass filter, its response at omega is equal to pi is non-zero, so it's a high pass filter. Therefore it also doesn't satisfy the criteria of being neither low pass nor high pass. So let us revisit our observation for the first case. When hn is odd, satisfies these two property of being odd symmetric and of odd length, then we see the filter we obtain has a frequency response of 0 at both omega is equal to 0 and omega is equal to pi. Therefore it's neither a high pass nor low pass filter, which is, by the way, a type 3 linear phasifier filter. The second option, hn satisfies the property of even symmetry and even length, which is a type 2 linear phasifier filter. Here we see the spectrum response to be 0 at omega is equal to pi. Therefore it satisfies the criteria of being not a high pass filter, but its response at omega is equal to 0 is non-zero. Therefore it is a low pass filter. So again it doesn't satisfy the criteria in problem of being neither low pass nor high pass at the same time. The third case, we see the impulse response have this property of even symmetry and odd length. Here we see that frequency response at omega is equal to 0 and omega is equal to pi are both now have non-zero values. Therefore it is a all pass filter. So it also doesn't, of course, it is just another extreme of the it's just on different completely opposite side of the filter behavior in question, which is supposed to be neither low pass or high pass. It's actually all pass filter. It's just complete opposite, extreme end. So therefore it is not also our solution. The second one is also not. The first one is, and the fourth one we see again that its response at low frequency, that omega is equal to 0 is 0. Therefore it satisfies the criteria of being not a low pass filter, but again its response at omega is equal to pi is non-zero. Therefore it's a high pass filter. Therefore this also fails. So it turns out eventually the first case we have considered is the filter we need, and this corresponds to odd symmetry and odd length. Therefore the first option is the correct one. Okay, next we move to this block diagram. This we have seen in lecture. This corresponds to M channel maximally decimated filter bank. Of course here M is equal to 2, you can see only 2 channels here. So these two filters, see that xn is same signal, xn is fed to G0Z and G1Z. The purpose of this filter to perform analysis. So these two are analysis filter, and here you perform downsampling operation. This is intermediate sequence V0 and V1N, and this then you perform upsampling. Then you have these two filters whose outputs you are combining to get x hat of n. Therefore these two filters correspond to synthesis filter. Why I am calling this synthesis filter? Because this filter's output you combine to get a new signal. That's what it is called, synthesis filter. Just for the opposite reason, this is analysis filter, because you are feeding these two filters the same input, which is supposed to analyze the spectral behavior at two different band maybe. That's so here we get a x hat of n, which is a estimate of xn here, and also in question we see that z0 of z is equal to e0 of z square plus z to the power minus 1 e of 1 z square. If you remember from the previous lectures and also from the previous problem solving session, we have held that it is nothing but type 1 polyphase this is nothing but type 1 polyphase decomposition. Therefore the question asks that under aliasing cancellation constraint, this is important, and we are using quadrature mirror filter. We have encountered the concept of quadrature mirror filter in week 6 lecture in details. Then which of the following statement hold? Okay. So let us write down the information we have in hand. sending this signal xn through these analysis filters, performing processing operations, and these two branch output are fed to synthesis filter J0 Z and J1 Z, and the output of whose are combined to get a estimate of the original signal xn. So if you follow the lectures, the example is almost similar to what is been described there. And if let me write the Z transform of xn as xz and x hat n, its Z transform as x hat of Z, then we have seen that x hat of Z is nothing but the equivalent transfer function, which represents the entire block here, times the original spectrum of input xn, which is denoted as xz, and a aliasing component, which is also a function of flipped version of original input spectrum. We also remember that this we have denote as signal term. This is our effective signal term, or desired, what we desire, and this is the unwanted part, which we denote as aliasing term. Actually, we would be happy if x hat of z is this only and this part is not at all there, but this is inevitable part of this processing. Now when you do this multi-rate signal processing, this is supposed to appear. So your main goal is to design the synthesis filter, analysis filter in such a way such that this aliasing term vanishes. Now let me focus on the aliasing term here once more. Aliasing term, if you see, is product of az times x of minus z. You cannot you cannot modify or change the original input spectrum. It is as there it is, and it keeps changing with your input signal. So that's not really your concern. Your concern is to design that az such a way such that this product becomes 0. In intuitive sense, if you see that if this spectrum of az and x of minus z, the flipped spectrum of original input signal, are non-overlapping, that is they cover different bands or different parts in frequency domain, then also aliasing term goes to 0. But that's actually not the concern here, because your x of z keeps changing, so you need to design your az in such a way such that your aliasing term goes to 0 for all xz, not specific to this x of minus z. So the argument I have given exactly now is not really true. Your az should be 0 irrespective of the original input signal, because in that case only, for any input signal, your aliasing term is going to 0. So let us see. We have also seen in the lectures that this transfer function tz is denoted as this: product of analysis and synthesis filter at the first branch as it is, and so does in the second branch. Where the AZ is a slightly modified version of this, flipped version to be specific, which is J0 of Z, G0 of minus Z plus J1 of Z, Z1 of minus Z. So this specific term that is mentioned here, aliasing cancellation constraint, let me write down here, aliasing cancellation constraint. This corresponds to AZ to be 0. Now how can you make AZ to be 0? If you see from this equation, let me denote it as 1, this is 2. If you choose J0Z as G1 of minus Z, so let me correct myself here, G0 of minus Z and Z1 Z as minus, sorry, it should be G1 here, yep, and J1 Z as G0 minus G0 of minus G0 of minus Z, then you put this in this expression, and then it becomes, this results into AZ is equal to half times, in place of Z or Z you put G1 of minus Z, G0 of minus Z, and then J1, this minus term comes here, G0 of minus Z, Z1 of minus Z. So you see this goes to 0. Now AZ goes to 0, that means your, irrespective of your original input spectrum, your AZ is going to 0. So no matter the signal you feed in here, at the output you are only going to have this signal term, some effective transfer function times original input spectrum, but no aliasing term would be present. For that, this criteria has to be satisfied. So when we say, let me write down in the next slide, okay, so we have just shown that AZ0 requires satisfaction of this property. Your Z naught Z should be G1 of minus Z, that is your analysis filter on the, sorry, your synthesis filter on the first branch should be the flipped spectrum of the analysis filter on second branch, and the synthesis filter on second branch should be negative version of the flipped spectrum of synthesis filter on the second branch, which is Z1 of Z, should be negative version of analysis filter on first branch. And we have another property here, quadrature mirror filter, which we'll see in details in next problem. We'll just use a mathematical expression here, quadrature mirror filter. Okay, let us discuss here itself. The question says that quadrature mirror filter, therefore Z0Z and Z1Z are really quadrature mirror filter pair, and that satisfies this property. This is because if you remember the quadrature mirror filter spectrum, let me write down here. Suppose this is H0 of Z, then is quadrature mirror counterpart, quadrature mirror counterpart is going to have frequency response like this, and this is H0 of minus Z. And this is symmetric about this frequency pi by 2, since pi by 2 is 1/4 times 2 pi. This is the source of the name quadrature. What is the difference between H0 of Z and H? Let me write it down again. You can see this blue filter is nothing but a shifted version of H0J and flipped and shifted. Because if you denote as H1 to the power j omega, As you can see, it's a shifted version of the flipped, actually it's a shifted version of h naught of z, the shift pi. You can see if we denote the quadrature meter counterpart of h naught as h1, h naught can be obtained by shifting h naught to pi here. We obtain to the power j omega minus times at the power minus pi. H naught of minus z. Okay, that's not really concerned here. So we have obtained these three things in this context. Let us focus here. We have these three things. J naught of z is equal, sorry for this error, z naught of z is equal to g1 of minus z, j1 of z is equal to minus g naught of minus z, and g1 of z is equal to g naught of minus z. If you put this here, this would result into j naught of z is equal to g naught of z, and if you put it here, it results into j1 of z is equal to minus of z naught of z. Anyway, it's like minus of z1 of z only. So we have previously seen the polyphase decomposition of g naught of z given here. Z naught of z is given as e naught z square plus z inverse 1 of z square. Therefore the synthesis filter in first branch j naught of z is nothing but e naught z square plus z inverse e1 of z square, whereas j1 of z, if you put in the expression of z naught here, it's minus e naught of z square, minus term vanishes when you put square to it, and this is here, minus will come from this z inverse term, z inverse e1 of z square. This will result into z inverse e1 of z square minus e naught of z square. These are the expression of synthesis filter in the both branch. So therefore this expression is correct, this is not correct, this one is again correct. Therefore both 1 and 3 are the correct option. Therefore fourth option is the correct one. Okay, for the previous question it asked what are the condition for perfect reconstruction. So as from our discussion we already know that one condition for perfect reconstruction, one immediate condition actually, I should better say, one immediate condition is this az is equal to 0. So you might be very tempted to take the first option is correct, but let us also explore the other options. But first the perfect reconstruction happens. Let me write down the expression here again. X naught of z is dz xz plus az x minus z. X sub minus z. So even if this term goes to 0, that doesn't ensure that you can recover xz completely from x hat of z. For that, this tz, this transfer function, should have some structure. Like, think intuitively that, let me write it down, a statement also. Perfect reconstruction is only possible if x hat of z is only the shifted and scaled version of xz. So perfect reconstruction only shifting and scaling operations can be tolerated. Now these are the operations that are, you can find analogy between linear time invariant system, LTI system. They are also, you introduce this two kind of operation, only shifting and scaling, because you can see in a intuitive way that if your estimated signal x hat of n is only a shifted and scaled version of the input signal, then you can perform the reverse operation. Like if it is a delayed version of original signal, you advance it, and if it is scaled operation, you can proportionately attenuate or amplify it. These all are linear operation, LTI operation you can perform, and you can get back xn in a proper format. But if it's not, if it's something beyond shifting and scaling, some time variant operation, then perfect reconstruction of xn is not guaranteed. So only up to this operations are allowable, such a in a way that your overall transfer function, the impact of that should not be more than shifting and scaling. This is a time invariant operation. You can get back your original signal by appropriate processing on receiver side if only shifting and scaling is happening, but otherwise it is not guaranteed. So in a mathematical way, how does that appear? Your x hat of n is allowed to be some scaled version a times x of n minus n naught, some delay or advance operator, whatever it is allowed. In a z transform, we take z transform both sides, it becomes x hat of z a z to the power minus n naught x of z. So your transfer function should be of this form only, a z to the power minus n naught. Now let us move the question. Okay, questions here only. So which of the option matches? You see the second option corresponds to tz is equal to z is equal to minus n naught. If you compare these two, you get a is equal to 1, scaling factor to be 1. So therefore this is a correct option. So your for perfect reconstruction, not only az should go to 0, but also your effective transfer function should be of this format only. Therefore the fourth option is correct, both 1 and 2. Let's move to our sixth question. Quadrature mirror filter. We have already studied the properties in the lecture and also previous question. Which says that this quadrature mirror filter pair is given by H0 of Z and H1 of Z. This is a pair, QMF pair. Then H1 of Z, which is we are supposed to find in this question, should be a response H0 of minus Z. This is QMF property. QMF property. We have also drawn the frequency spectrum there in the previous question, somewhat like this. If this is the response of H0 of Z, then this QMF counterpart have response like this, H1 of Z, which is H0 of minus Z, a shifted version by pi, and there is a symmetric corresponding to frequency pi by 2. This is pi here. So if H1 of Z is equal to H0 of minus Z, you take inverse Z transform to get corresponding impulse response. H1 of n is equal to minus 1 to the power n Hn. This is basic Z transform property. So you obtain your new impulse response, that is the QMF pair of H0. The filter H1 impulse response is related to the impulse response of H0 of n as follows. Now you can see when H0 Z is type 1 linear phase, correct? That means H0 of n has even symmetry. And what does even symmetry mean? Your H0 of 0 is going to be H0 of n minus 1 for length n, H0 of 1, H0 of n minus 2, like that, correct? So if I write down the Z transform in terms of impulse response, which is like H0 of H0 of let me correctly write it down. H0 of 0, H0 of 1, Z inverse dot 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 H0 of n minus 2, Z to the power minus 2, plus h naught of n minus 1 z to the power minus n minus 1, correct? And we can use this property to write it as h naught of 0 plus h naught of 1 to minus 1. These values are just going to be repeated from the end like this. So if you draw the impulse response of h naught of z here, you'll obtain the follows. These values are just going to repeat. The first and last coefficient are same, the second and second last, and so on. It basically is symmetric around the center, mirror image of each other if you take them, put the mirror across the center. Now let us, okay, I think need to introduce a new slide here. Okay, we have seen the expression of h1 of n to be minus 1 to the power n h naught of n. This corresponds to h naught of n for n is equal to even, because your minus 1 to the power even number is 1 only, and minus h naught of n for n is equal to odd. By the way, here type 1 linear phase have this even symmetry and length n to be odd also. So if I write h1 of n, this sequence, it turns out like this: h1 of 0, h1 of 1 up to h1 of n minus 2, h1 of n minus 1. And this, if I am willing to write in terms of h naught of n, the symbol corresponds to h naught of n, the coefficient corresponds to h naught of n, it becomes the even indexed coefficient remain the same, the odd index get their signs flipped. By the way, the let me show you the type 1 here. Okay. You see, for type 1 you have even symmetry and order is even, therefore your length is odd. Okay, your length is actually n is odd, therefore type 1, you see your length is n is equal to odd, therefore index n minus 1 is even, therefore its sign doesn't change, it is just h naught of 0 here. The previous one, however, n minus 2 is odd, therefore its sign changes, it becomes h naught of 1, like that. Okay, if you have problem in understanding in this step, let me clearly write it down. You can relate to first two things because index are pretty much visible, but for these two you may have difficulty understanding. So h1 of n minus 2 corresponds to minus 1 to the power n minus 2, h naught of n minus 2, and last one corresponds to minus 1 to the power n minus 1 times h naught of n minus 1. And since n minus 1 is a even, because for type 1 filter length n is equal to odd, therefore n minus 1 is an even number, therefore it becomes h naught of 0 minus h1 of 1 here, like that. This becomes minus of h naught of n minus 2, since n minus 2 is odd, this becomes h naught of n minus 1, and we can now write it in this manner: h naught of 0 minus h0 0 of 1 comma minus h0 of 1. This is from the property of the impulse response of h naught n itself, and this is h naught of 0. So the let me draw the impulse response here for h1 of n. h1 of n, it starts with, if we compare to previous response, h at 0th index, that will remain unchanged, at odd index 1, it gets flipped. Yeah, it gets flipped. Similarly, from the last two, we see at n minus 1, this is at n minus 2, here also it gets flipped, minus h naught of 1. So still corresponds to the center point, it remains even symmetric only. So you can see h1n is also even symmetric, and the length n is odd, therefore order n minus 1 is even. Therefore h1 of z, which is the QMF pair of h naught of z, is also type 1 linear phase FIR filter. Let us move to the next question. It's the 7th one. You have to design a low pass filter with specification. Your pass band spans from 0 to 80. Okay, let us draw the response of this low pass filter. This is like this. So this corresponds to pass band edge, and this corresponds to stop band S, and in this middle you have this transition band. We have seen this in lecture multiple times. So it says that pass band spans from 0 to 80 Hz, therefore WP is the pass band edge, which corresponds to 80 Hz, and stop band spans from 100 to 250, therefore WS is 100 Hz. Therefore, what is the transition band width? You can see this is nothing but WS minus WP, which is 100 minus 80, which is 20 Hz. Your normalized transition bandwidth is nothing but transition bandwidth divided with the sampling frequency. Normalized transition bandwidth is transition bandwidth over sampling frequency, which you obtain as 20. Sampling frequency Fs is 500. Therefore we obtain 2 by 50, 0.04. Therefore the fourth option is the correct one. This question asks what is the passband frequency of a two-channel quadrature mirror filter bank. The stop band frequency is 0.58 pi. Okay, for that we need to draw again the quadrature mirror filter pair. Let us draw it. Let us denote as h of z. Let me draw the other one in different color. And this should be a straight line. Forgive my drawing. 0 pi. They are symmetric around this frequency pi by 2, and one's passband also corresponds to others stop band. You can see this is WP, passband for HZ, which is stop band for h of minus z, whereas this stop band for h starts from WS, which is the passband h for h of minus z. Therefore these two gaps, this pi, but since this is symmetric around pi by 2, these two gaps are also same. This omega p to pi by 2 and pi by 2 to omega by s. Not only that, this gap, which corresponds to 0 to WP, though it's not very much visible in the drawing, this should be equal, because this is just a mirror version of each other with respect to the frequency pi by 2. Therefore their pass bandwidth and stop bandwidth are equal only. This is pi. So this gap is denoted when we said as omega p minus 0, which is equal to this gap, which is pi minus omega s. Therefore we have this equation, pi minus omega s. Now this stop band frequency is given as 0.58 pi, and we need this pass band frequency omega p. So we obtain this as 0.pi minus 0.58 pi is 0.42 pi. Therefore the pass band frequency for this two channel quadrature mirror filter bank is 0.42 pi. This is the 8th question of today's session. So with this I end today's session. We'll meet again for a 7th problem solving session on next Tuesday. Thank you all.